Hello, and welcome back to our online review sessions, or recorded, I guess I should say. Congrats again on making it through the third exam. Today we are going to go through some questions from that, mostly the ones that you guys asked about during the actual exam, and then we'll do some example reactions from chapters 4 and 5. So know that there may be some we haven't covered yet, and there's others that should be familiar, but they're all going to be lumped together in the end, and I'll give you two reactants, and you'll come out with some products. And so, without further ado, let's get to it. So you guys will get this back next week, but I'm going to go through some of the questions again that you guys had. We'll start with some easier ones, we'll move on to the harder ones, and know that if you have any more questions, you're always welcome to come to me. So let's start actually with one out of number 1. So here you were asked to calculate the number of moles for each compound that was listed, and the first misconception was just that whether you needed to calculate the number of atoms or moles of each element, which you could do, but you're not asked for in this question. So we'll do just a little bit of review here and move on to some of the more challenging ones. So let's do the more challenging of the two. Here you have 6.8 grams of sodium chromate. And so you can see here, right, if the goal is to go from grams to moles, you're going to need to use essentially what's known as the molar mass. And here the molar mass refers to the weight of one of these compounds, right? So we'll need to add up all of the individual pieces. Just like for the mass of a human, you'd add, say, the body, the arms, the legs, and the head. Here we're going to add 2 sodiums, a chromium, and 4 oxygens. And so you'll turn to your handy periodic table. And so for sodium, we know, for example, that that is 22.99, right, grams per 1 mole of sodium in this case, and that we have 2 of them as well. We also then have a chromium atom, and so we'll look down, that's one of the transition metals in group 6 here, and that'll be 52, and we only have 1 of those. And then next we'll add 4 of these oxygens, and that's going to be 16.00 times 4. So the first step will again just be coming out with that molar mass, and that's going to be grams per mole of the compound that we have, so sodium dichromate. Sorry, just sodium chromate here. And so again, always turn to your best friend. 22.9 times 2, it's going to be 45.8. And we're going to have, well, 52, right? That doesn't change. And then we're also going to have, in this case, should be 64. And it still is, isn't that nice? So we're going to add all of these up. 64 plus 52 plus 45.8. We get to 161.8. Right? So for 1 mole of these, we're going to have this many grams. And so now what we're going to be able to do is just set up our conversion, and we'll see that it's not so bad. We'll use these ideas later on in the test as well. So we'll start with the given, right? We only have 1 amount here. So in this case, it's 6.98 grams of sodium chromate. And again, I always recommend including what the compound is, because later on we'll be working through different ones and translating those, and so it's kind of helpful to have. We know that we want our answer to be in units of moles. That's what the question asks for, right? Moles of the sodium compound. And so if we want moles, we're going to need that out on top. And then we're going to also have the name of it as well. And then a couple things to note. One is that the units that we've come up with have a relation between moles and grams, so we might know to put grams on bottom for that reason, or we can also think about canceling out this in just a moment. So we'll put grams of the sodium chromate. And then again, the hardest part is figuring out where we put the value we came up with. And so again, we're thinking that this is 161.8 per 1 mole. So we can put the 1 mole on top here and the 161.8 down on the bottom. And so if we put that into our calculator, pretty simple, right? 6.98 divided by 161.8. We're going to come out with, in this case, 0.0431 moles of this compound. which makes sense, right? We have around 7 grams, and the whole thing, 1 mole, weighs around 160, so it's a small fraction, and we can see, right, this is much less than 1, and so that's going to be a good answer, including not only the units, but the compound as well. And we'll translate some of those in just a moment, too. So that was one of the examples of question 1. Now let's look at one of the others on the first page. We'll look at question 2. So this one might have been a little tricky. We may not have seen it exactly in this form, but you guys have all the tools to answer this question as well. The premise here is that we want the number of moles of sulfur that essentially react or will combine that react to form the product Al2S3. So now we have a ratio of the number of moles for each. And they essentially react with, in this case, 0.225 moles of aluminum. So, right, we have a couple things here. We have a given, right, an amount that's specific to the problem. We have a conversion factor. It doesn't look like there's numbers in there, but we know that there are 2 moles of aluminum for every 3 moles of sulfur. And we know that we want moles of sulfur out. So again, let's start with our given. And let's work to what we want. And so we'll start here with 0.225 moles of the aluminum. And then we can actually go almost straight to, in this case, right? I did ask for moles. Yep. We want to essentially relate aluminum in this case and sulfur. And so we'll use this conversion to help us. And so, right, if we're going to get rid of moles of aluminum, and we are going to go to moles of sulfur, we know that, again, in this compound, we're going to have a relationship of 2 of the aluminums per 3 of the sulfur. And then what else do we need? Well, we've actually already figured it out, right? We have our units that cancel. And then we also have the units that we want. And so in this case, all we need to do is figure out really that ratio or that relationship between the two. So 0.225 times 3, and then divide through by 2, and we get around 0.338 moles of sulfur as our answer. Right, and so the question was, we know that if you had 1 mole of these, you would have 2 atoms or 2 moles of aluminum and 3 of sulfur, but here we have less than that, and so it's kind of just asking if you have a portion, what is the other portion you come out with? And right, we can see there's a 0.2 amount roughly of the aluminum, and we get out a 0.3 of the sulfur, and so that makes good sense. And so let us keep going. Pardon me for the pause. I'm trying to think. Let's do question 5a, and then we'll do question 5b as well. And then I think we'll do the balanced ionic and net ionic, because that's going to help us with some of the next problems in chapter 4 and 5. Also, just a reminder that this week, midterm grades are due for me, so I'm going to be calculating those and submitting them online. If anything stands out, I'll of course reach out to you, and know that if anything looks weird, of course reach out to me as well. But again, this is only a temporary grade, right? This doesn't go on your transcript, and there's still a lot of opportunity to, well, either improve or not improve, I guess. So know that there's still chances to come and ask for extra help or actually try some of these problems as well. But I'll stop talking about that now. So here we have an equation that's been balanced for you, right? Something you've seen before, maybe you'll also see in a bio course if you're maybe a pre-med or something like that. We're going to be taking essentially a different form of the combustion equation you've seen before, which we know gives out CO2 and H2O. And right, even though it's not balanced just yet, and you did get it balanced, we can see, right, there's 6 carbons, so we might expect a 6 here as well. And then what we'll find when we balance is there's a 6 in here. And so in this problem, your given is going to be that you have 1 grams of glucose. And the question is going to be, how much oxygen do you need to completely react it? And so if I asked you if you had 1 mole of glucose, how many moles of oxygen do you need? You would say that you need 6. But it's harder to say the relationship between grams of glucose and grams of oxygen because they weigh different amounts per mole. And so in this case, we're going to need to translate this first to moles, and then relate the 6 and the 1, and then bring this back down to grams, because what we want here are going to be grams of oxygen. And again, just to be clear, when we refer to oxygen here, we're talking about O2. But if you did make it all the way and got to O, you'll probably get some good partial credit for that too. So let's set this up, and you'll see it's pretty similar to the ones we've been working through in class. So we start with 1 grams of glucose, which I'll abbreviate GLU for right now. We may not know what steps in between. We know we're going to use molar masses. We know we're going to use some relationship between the moles of these two. But let's finish, I guess, by writing what we get out. We know that we want the grams of O2 as our answer. And so let's think, right? We're going to go first through moles. That's the whole point of what we're doing here. And a way to relate those two. Right? So the first thing we're going to look at, again, is that molar mass, right? We know we want to get rid of grams of glucose. We know we want to go to moles of glucose. Similarly, the next step will be going from those moles of glucose to the moles of O2. And we'll put the numbers in just a moment. And then the last step is going to be going from those moles of O2 to the grams of O2. And you'll see this is pretty much the basis for most of what we do in Chapter 3, and then go into Chapter 4 with things like solutions and stuff that we talked about just yesterday. And so now we'll figure out what we need to fill these in. Let's start with maybe an easy one. What's the relationship between moles of glucose and moles of O2? Well, that's going to be given by our equation, right? 1 of these glucose moles will give us, will require 6 oxygens. So in this case, we have a 6-to-1 ratio. Maybe we'll start with the oxygen over here, and we'll see that, say, 1 mole is how many? Well, again, each of these are going to be 16, and we have 2 of them, so we'll have a mass of 32 grams per mole of oxygen. And so last but not least, we have a slightly harder one to do, right? We want to know how many grams 1 mole of glucose is, and so let's think about what the molar mass is in this step. So the molar mass of glucose. And right, we know we're going to calculate the sum of all of the values of each of the atoms. And so in this case, first let's put in the number of each. We have 6 carbons, we have 12 hydrogens, and we have 6 oxygens. And then we'll put in the masses as well, right? So we know that in this case we have 12 grams per mole of carbon, we have 1 gram per mole of hydrogen, and we have 16. And so we might be able to see, right, we have 72 up here, we have 12 over here, and when we add in the oxygen, we'll find that we come up with 180 grams per mole of glucose. And so we'll add that 180 down here, and we'll see in a moment that we actually come up with kind of a funny answer, right? You can see we have a 6 times 30, which is around 180, a little higher, and we have 180 on the bottom. And so we'll find that the answer is actually pretty close to the amount of grams that we put in. And so let's figure that out. Let's do that for real. We're going to have, maybe we'll do it in 2 steps, right? We'll figure out what's on top and what's on bottom. So we have the 32 by the 6. That's going to be 192. And then we're also going to divide that by 180, right, from what's on the bottom here. 192 divided by 180. That's going to be 1. And then with our 3 significant digits would be 1.07. So it's kind of neat, right? Even though glucose is very heavy, you also need lots of oxygens, right? And so in this case, 1 gram of glucose, or sugar you might think of it, is going to require 1 gram of oxygen. So maybe that's why this reaction is so important to life, right? There's a balance in terms of the mass, something you engineers will well understand in the coming years. And so if our first problem in this, 5a, was looking at how many grams of O2 you need, the second problem is asking that if you have 1 gram of glucose, which we did in this previous problem, and we only get out, or we only use, right, the given here is 0.62 grams of O2, the question is, which is the limiting reagent? And so this was actually a pretty easy question if you already calculated your answer here, right? 1 gram of glucose requires around a gram of oxygen. In problem 5b, you only have 0.62 grams, so you don't have enough, right? In this case, you can think of there not being enough oxygen in your engine, or in this case, being breathed. That would be really bad. And so in this case, the oxygen is the limiting reagent. And again, you're going to know this just because it is less than the amount of required oxygen to react fully. And so you could imagine, right, that if you only had, say, half of a gram or 0.5 grams of glucose and 0.62 grams of O2, that this would be in excess. But in this case, right, because you have less than 1.07 grams of O2, the glucose will be in excess and the O2 will be limiting. And so that's some of the harder parts of this last exam. Let's do a balanced equation, and then we'll jump into some reactions, which is what I like about this class, right? You begin to learn about how you can predict what happens just by knowing the identity of some of these things. Okay. So the good news here is that I was able to give you not only the charges, but you also had the full equation. Soon, what you guys will be expected to do is come up with the products as well. So I'll give you just the reagents, and maybe we'll do that here just a little bit, right? We have iron nitrate, and that's going to react, well, that's aqueous as well. That'll be important. And that's going to react with lithium hydroxide, which is also aqueous. That is going to transform into the products, which we'll figure out in just a second. In terms of identifying what we have here, right, we have a salt, and we also have a strong base. And so, right, we don't necessarily have an acid and base. We don't necessarily have, like, 2 strong electrolytes, though I guess these might be considered those. And so something we'll find is that we're going to do this double replacement. You also had this on your exam. And so in this case, the lithium swaps with the iron, and you would get lithium nitrate. And then you would also have iron hydroxide. And so the lithium nitrate here is going to be aqueous. That's going to dissolve pretty well. But we'll find if we look at those solubility rules, which we'll use for the next exam, that this is going to be a solid. This will not dissolve. And so really the whole point of this reaction is that you mix 2 soluble things together and you come up with the weak electrolyte. So I guess this is a good example of that. Right, and we're going to always think of a weak electrolyte as something that doesn't dissolve well. Because it's a solid here, we can see that that's the case. And right, so here we asked for a balanced ionic and net ionic equation. Though this is the molecular equation, you probably want to balance it before you get started, just so that there is no confusion there. So let's do that first. Couple things, right? Just looking at it generally, we can see we have 3 nitrates and only 1. We can see we have 3 hydroxides and only 1 here. So probably some 3s will pop up. The good news is, right, that at the moment, the irons are balanced and the lithiums are balanced as well. So we'll maybe start with some of those polyatomics, those anions that have several atoms in them. And so let's see, well, if we have 3 hydroxides here, let's add a 3 in the front of the lithium, so that now we have 3 of these as well. No surprise, right? Now we have 3 lithiums, and so we'll add a 3 in front of here, and then conveniently we balanced our lithiums, and we also now have 3 of these nitrates to balance with the nitrates here. And so a question I might ask is, what is the molar ratio of iron to lithium? Here you can see there is a 1 to 3 ratio. That's conserved in the end, right? We have 3 and then 1 here as well. So this would be your balanced molecular equation. The next step is going to be coming up with our ionic equation. And again, the premise here is that we're going to take anything that is aqueous, anything that does dissolve or is a strong electrolyte, and we are going to separate it out. And yet our solid product, which doesn't dissolve, will remain in that compound. So we'll make sure that it stays in this form. You'll write it almost exactly as you see it here. And so let's start with the iron. We know that that's going to separate from the nitrate. We also know that we have 3 of those nitrates. And so now the question comes down to charge. One way that you could do it in this problem is, for example, knowing that lithium is a group 1 metal. So all the way on the left side of the periodic table, we can look at it here, just right over here. We would know that has a charge of +1. And so if we look at this compound, we can begin to see that if this is +1, this must be -1. And that's going to stay the same. In Chapter 5, we'll talk about oxidations and reductions, but for here, charges aren't going to change. So we would have a -1 charge here. Because we have 3 of these, we know it's balanced with the iron, and we would have a positive charge there. Now again, I gave those to you on the board, but now we're moving to a chapter where you're going to start to figure these out for yourselves as well. Okay, so we have the first component, and we'll add that they're both aqueous as well. We know that because we were able to separate them, and they're going to do some chemistry, right? That's what this equation's about. Let's add the second component. We know we have 3 lithiums. We know that's a +1 charge. We know that it's aqueous as well. And then we also have 3 hydroxides, which will be aqueous. So that's the left half of the equation. Now let's look at some of our products. And you already know that we're going to get some of these on the right side as well, right? We're going to cancel them out in just a moment. And so let's break down the lithium nitrate. You may look at the solubility rules and realize that lithium is soluble as are nitrates, so this is definitely a strong electrolyte. And so in this case, we're going to have 3 lithiums, which are aqueous. We're going to have those 3 nitrates, right, to balance what's on the left. And those are going to be aqueous. Let me just erase this weak electrolyte here for a moment. And now the question really becomes, because this is solid, do you separate it? And again, it's a weak electrolyte, and so it won't. And so we'll write it just as it is. Don't even need to worry about charges, because it's already balanced. And so, right, this is a complete ionic equation. And now what we're going to do is identify the, the spectator ions. And so again, spectator ions are going to be things that don't participate in the reaction. They're only on the left and the right equally. And so in this case, we're going to see that, for example, we have nitrates on the left and the right. We have lithium on the left and the right. But you'll notice that the iron isn't iron 3 on the right-hand side, right? It's in a compound. Similarly, the hydroxide is not free. It is in a compound. And so the good news is that as you move to your net ionic equation, really all you're going to do is take anything you've underlined and leave it on the side. So let's say start with the iron plus. Starts as aqueous. We're going to add those 3 aqueous hydroxides. And then, right, we're removing the lithium and the nitrate, and so we'll end up here with our iron 3 hydroxide. And I'll make sure to put that into solid. And now we can kind of see, right, if you were looking at your starting reaction, you might not be able to tell what's important. Down at the bottom, we can see that really the chemistry that's going on is between iron and the hydroxide. You could imagine maybe switching out the nitrate for chlorine or another anion. Similarly, we can imagine the lithium isn't as important. Maybe this could be sodium or potassium as well. And so know that this is what I'd be looking for. Definitely partial credit for anything that resembles what we have in the middle. Also partial credit if you didn't include, say, some of the designations for the phase, aqueous, solid, things like that. Otherwise, yeah, definitely also partial credit for perhaps a not perfectly balanced equation. But I don't think that's too bad. So those are some of the harder ones from the third exam. And we'll see, I haven't finished grading yet, so I'll let you guys know how it went. But know that this was pretty representative of what the latter half of the course will be like. A little bit of math, a little bit of critical thinking, and so we'll continue to practice problems like these as well. Okay, so we're done with our sort of brief review of exam 3. And so now let's look a little bit into problems from chapters 4 and 5. These are actually not going to be taken from the book. I borrowed these from Dr. Colts, who actually runs the general chemistry sections. And so these are ones that he's compiled and he thinks are really good examples of what you guys should know in this course. And so we're going to first look at what we call those precipitation reactions. Which we've already done, right? That last example was iron precipitating out in the form of a hydroxide. And so in this case, we're going to take a variety of different salts and try to see what happens when we mix them with chlorine. And so we'll see in just a second how that works. We're going to start with magnesium chloride for each. Something you'll notice is magnesium's in that second column, so it'll have a charge of +2. Chlorine, we know, is always -1, and so to balance, we need a 2 here as well. This is going to be, again, part of like the road salt, for example, that they put down when it is snowy. It's not been snowy this year, or icy, I guess. And then we're going to react this with a couple of different things and begin to see what the differences are between those reactions. So in a moment, we'll add in the other reagents after I pick some of the better ones for us to work with. Okay. So let's do one let's do one with a strong base. That's our sodium hydroxide. We know it's strong for a couple reasons. It's on our list. We also have a strong electrolyte. We have the sodium dissolves, the hydroxides generally don't, except with group 1A metals. We're also going to have, let's do the sodium sulfate. And we'll add in the phases in just a moment. We're also going to have, in this case, trying to think of a good one. Oh, here we go. Let's do sodium nitrate. And then last but not least, let's do one with a sort of big polyatomic, right? So maybe we need to do some balancing. In this case, we'll look at sodium phosphate. And so even before we start, let's look again at some of the stoichiometry of just the compounds. We'll balance our reactions in just a moment. Here we can see, for example, that we have a -1 and +1 charge. Sodium will be the same for all of these. So here we have +1 twice, right? That's the 2, and so this will be -2 total. This will still just be -1 from our last example. And then the phosphate's the big one. That's really the biggest you'll see in this class. And that'll be -3, right? Balanced by those +3. And so let's take a moment to figure out if things are soluble. Because these are precipitation reactions, you might assume that all of these are, or else really nothing would happen, or could happen. And so we will put aqueous for each of these. If magnesium chloride is aqueous in the first example, it will also be aqueous in all of them, right? This is a property that's intensive. It's going to be relevant regardless of the situation. We know that the sodium hydroxide, because it's a strong base, is going to be soluble. Similarly here, we're going to find that the sodium salts, because that is part of group 1, will always be. So the good news is that we're not trying to do any reactions with anything that isn't soluble. That would take probably a very long time. And so now we can begin to think about first what our products are, and then balancing, and then we'll be good. Okay. So let's see. In the first one, you can see that we have, again, a salt and a base, kind of like our last example. So maybe this is best to think about in terms of electrolytes. In terms of the products, you can again guess that all of these are going to kind of flip. And so we'll begin to see what's going on. So we'll put the sodium with the chlorine, the magnesium with the OH. And so in this case, let's look at some of our products, right? We're going to have magnesium. We're going to have a hydroxide. We'll balance them in just a moment. And then we also are going to have sodium and chlorine as well. So first thing is we know that magnesium is +2. We can see it in the compound on the left. And so if this is -1, which will always be that hydroxide, we're going to need 2 of those as well. So now let's just do a little balancing. If we have, say, 2 chlorines on the left, we're going to need 2 chlorines on the right. And then we'll need 2 sodiums on the left to balance that. And then you'll notice we have the 2 hydroxides we need to balance here. So we can see a 2-to-1 ratio of sodium to magnesium in this example. Makes sense, right? The charges are also, 1 to 2 in this case, so it balances. So now what we want to think about is what are the phases of these products. And so we'll start with example with sodium chloride. This is going to be a good one to always begin with. We know that table salt is soluble. Also, again, we have a group 1 metal and a halogen. These are generally going to be soluble. So we know that this will be not our product, right? We're talking about precipitations. And so here we have to think about the other solubility rules. Here we have the rule that hydroxides are going to be insoluble, except for group 1 metals. And because magnesium is a group 2 metal, in this case, we're going to have our solid or our precipitant, if I could spell. And so in this case, not only did we balance, we came up with the phases, and which is our product. And so that first one looks pretty good for us. Looking at the second one, let's see what we have. Well, let's do the flip again, right? We know that we're going to get, for example, sodium chloride again. And so the question is going to become, what about the magnesium sulfate? And so in this case, we're actually not going to have any reaction that occurs. And so we know already that the sodium chloride is going to be aqueous.